let's just, okay, so normal approximation to the binomial. So recall that the binomial situation arises in situations of independent repeated trials, so the probability doesn't change from one trial to the next, where the outcome of each trial, there's only two outcomes, hence binomial, called success or failure. And recall that the formula is equal to this. The graphical representation of a binomial distribution with n is 15 and p equals 0.04 is shown below. And so notice they were kind enough to do all the calculations for it. We graphed it, the probability versus your x value, right? And notice that it takes on, notice that this binomial situation, even though it's very discrete, takes on the shape of a normal distribution. So this suggests that we can approximate a binomial distribution by a normal distribution. The advantage of this situation is that we do not have the tedious task of calculating binomial probabilities. So here's an example. Let's just suppose n equals 600, and we needed to know the probability x is less than 200. Oh, well, if the probability x is less than 200 equals probability of 0 plus probability of 1, can you see how we would have to do 200 calculations? 200 calculations. This is too much. Too much, right? Too much. The normal approximation to binomial helps simplify such tedious tasks. But there's several steps involved. And each step is worth a mark to you on the test. Okay? Just so you know. Step number 1. Determine whether or not the normal approximation is appropriate. The products of NP and NQ must be at least 5. So, these are the conditions. NP is greater than or equal to 5, and NQ has to be greater than or equal to 5. If they're not, true, you cannot use the normal approximation to the binomial. You'll just have to use binomial. Okay? You cannot use, right? So these two conditions have to be true. Good? Okay, when NP and NQ are not at least 5, the probability distributions are either skewed to the left or skewed to the right and do not take the appearance of a normal distribution. So if it would look like this maybe, that's skewed left, or it would look like this, and that's skewed right. All right. The mean and standard deviation must be estimated using the following formulas. Do you remember expected value of x? That's just another way of saying mean, right? Do you remember when we took the binomial distribution, that's your mean, and this is your standard deviation, but I think the proof of this would be beyond the scope of this course, so you just need to accept that calculation for now, okay? So you need to be able to calculate the mean, which is just expected value, and your standard deviation. The third step, an adjustment must be made to account for approximating a discrete distribution by a normal distribution which is continuous. So there is always this 0.5 adjustment. There is always a 0.5 adjustment. So let's take a look at that because I want to make sure that you're comfortable with calculating it. I think I had more examples which I would like to do. Okay. So if the probability is less than or equal to 5, the adjustment is, because we want to include the 5, we have to go less than or equal to 5.5. So let's just take a look at this. Do you remember when we did a discrete distribution, we had our histograms like this? Just like, I guess that should be, maybe we'll call that 6. Okay? So do you notice that this value here would be 4.5? No, this value here would be 3.5. This value here would be 4.5. This value here would be 5.5. This value here would be 6.5. Do you agree? So if we want the probability it's less than or equal to 5, which is there, that's okay, then we have to go to 5.5 to get it all. Right? Can you see why we're going to 5.5? If we want the probability x is greater than or equal to 5, then we're going to have to go to 4.5. And if it's equal to 5, we're going between 4.5 and 5.5. Because for the normal distribution, which is continuous, you need an interval. Now tell me, what if we were going to do probability x is less than 5? That would equal to the what's our 0.5 adjustment? Do we want 5 included? No, 5 is not included, right? So we have to go to what? Huh? 4.5. Okay, if we want the probability x is greater than 5, then what? We'd have to go to, we don't want the 5 included or any portion of the 5, right? So we would have to go to, yeah. So there's this 0.5 adjustment that, which is worth a mark in itself. Sorry? Yes? Oh, this said greater than or equal to 5. This says greater than 5. So the 5 is not included. That's the difference. I just wanted to do some examples with greater than or less than. Okay. Question 1. The probability of tossing a head with a weighted coin is 0.3. If the coin is tossed 60 times, what is the probability that A? We want the probability, we're really looking 10 or fewer. Can we not look at our phones? Is less than or equal to 10. Agreed? All right. So notice, if we want the probability x is less than or equal to 10, that's equal to the probability of 0 plus the probability of 1 all the way up to the probability of 10. That's 11 calculations. 11 calculations is too much. It's like, give us a break here, for crying out loud. So let's test to see if normal approximation is appropriate. So we go NP equals, well, N is 60 times 0.3 equals 18. And that's greater than or equal to 5. So that's okay. NQ equals 60 times 0.7, and that equals 42. And that's greater than or equal to 5. Therefore, normal approximation is appropriate. That's good for a mark, okay? Number 2. We need to calculate our mean equals NP, and we calculated that already. That equals 18. Standard deviation is equal to square root of NPQ, and that's equal to 60 times 0.3 times 0.7, which is equal to the square root of 12.6. And I'm going to leave it like that so we're not rounding too much. Now we're ready to do our job. Probability that x is less than or equal to 10 is equal to, what's my 0.5 adjustment? Yeah, because we want the 10 included, right? And that is equal to the probability z is less than 10.5 minus 18 all over the square root of 12.6. Remember, take your z-score to 2 decimal places, right? Because your table is to 2 decimal places, so we're kind of stuck with the 2 decimal places. And if you were to look that value up, you would get approximately 0.0174. So, probability 10 or fewer heads are tossed is about 1.74%. Can I explain anything better? Oh, okay, the probability, are you referring less than or equal to negative 2.11 is equal to the probability z is less than negative 2. And the reason for that is, when you take integral calculus, you won't take that here at York Mills. The integral calculus is no longer in the in the high school curriculum, but the area under a single point, like the area under, let's say, yeah, is 0. So that area under a single point is 0. To find areas, we need an interval. We need to go from a certain point to a certain point. Okay? So if you accidentally drop that equal sign, I won't care. Because it's equal, right? In this case, it's equal. Okay. Exactly 20 heads are tossed. Calculate this using the binomial model and the normal approximation to the model. Okay, so let's do that now. Part B. Probability x equals 20. Now this is going to be using binomial. All right, is equal to 60, choose 20, 0.3 to the 20, 0.7 to the 40. And that's about 0.0931. If you just take my word for it, this is just a review from the last unit. This should be a 20, right? Well, let's use the normal approximation to the binomial. Probability x equals 20. Can you tell me what the adjustment would be? Sorry? Okay. 19.5 less than or equal to x is less than or equal to 20.5. Okay. So that's our adjustment. So that's equal to, again, we're going to be doing probability x is less than or equal to 20.5 minus the probability x is less than or equal to 19.5. Yes. No. No. Whenever you're to a continuous model, it's important here. No, this is now a continuous model. Here it's important. Here it's not important. Okay, so now we're going to go probability z is less than or equal to 20.5 minus 18 all over the square root of 12.6 minus the probability z less than or equal to 19.5 minus 18 all over the square root of 12.6 is equal to the probability z is less than, I can't believe that that's 0.7. The answer in my book is 20.5 minus 18 divided by the square root of 12.6. Let me try that again. 20.5 minus 18 divided by the square root of 12.6. Oh, it is 0.70. That's better. Minus the probability z is less than 0.42. Notice whether I put an equal or not, it doesn't really matter. And if you look up those values, we get 0.7580 minus 0.6628, and that is 0.0952. So notice they're not equal, but they're similar. They're equal to 2 decimal places, right? These are equal to 2 decimal places, so they're similar. In situation where it's not heart surgery or anything of life-threatening nature, this is pretty good, right? It's pretty good. Too much cell phone, not enough focus. Okay. Can you just put it away for now? It is estimated that 15% of the Canadian population is undecided as to which political party to vote for in the next election. If a poll is conducted and 1,007 citizens respond to the questionnaire, what is the probability that more than 100 of them are decided? Okay, so it's a similar question. So what's our first step? Oh, okay. Let x be the number of undecided citizens. Okay, good. What's our next step? Check to see if the normal approximation is appropriate. Okay, so NP equals, well, it's 1,007.15 is undecided, and that is equal to 151.05, and we know that's greater than or equal to 5. So NQ equals 1,007.15 0.85, and that equals an even bigger number, and that's greater than or equal to 5. So we can say, therefore, normal approximation is appropriate. Number 2. The mean is, well, we calculated it up here, it's NP, and standard deviation, square root of NPQ, is 1007 times 0.15 times 0.85, and that is equal to square root of 128.3925. The probability that more than 100 of them are undecided. Now, they're saying more than. So here we can't put an equal sign, right? It's more than 100. So our 0.5 adjustment is 100. And that is equal to 1 minus the probability x is less than 100.5. So now we just calculate our z-score. Square root of 128.3925 is equal to the probability z is less than negative 4.46. So what do we do now? Is 1 minus what? What's the probability z is less than negative 4.46? You tell me. It's off the chart. Sorry? Yeah. Huh? Yeah. Therefore, 100% probability, uh-oh, my spelling's gone to pot. Probability that more than 100 are undecided. Undecided. Uh-oh. Too little space. Undecided. Can I explain anything any better? One more lesson and the course is over. Almost. Besides tests and presentations and exams. Okay? One more lesson.